So this will be the first draft of my FYP presentation as a form of trial run. Good afternoon, professors. I am Zikin, and today I will be presenting Streamsight, my FYP project that I've been working on for the past year. This will be the flow of my presentation, starting off with the background to provide some information and introduction, followed by the gaps that have been identified from the literature review, the design of the solution, results, future work that can be considered, and some concluding remarks. So to kickstart the presentation, I'll be starting on the background. And let's start off with why recommender systems in the first place. And it has been shown to provide economic benefits to companies that have leveraged the use of such recommender systems in the form of boost in sales and user engagement, driving revenue up to by over 30%. Then our next question is, what is a recommender system? And to really simplify the entire system, what happens is that your user preferences and other supporting data is taken and then fed into a recommender system, which is an algorithm that would then compute the input and output a prediction of your most likely preference and to recommend a relevant item for you. And there are multiple different type of algorithms that have been developed over the years, the graph-based model or memory-based model. So the focus of this project is to design a toolkit to evaluate these recommender systems. And a toolkit really is to provide a unified framework to evaluate and to build recommender systems, be it for offline or production use case. And a toolkit typically follows such a pipeline. And the pipeline is as follows. We will first load the data and pre-process whichever data set that is needed in the offline setting. We then split the data, followed by the training of the recommender system, the evaluation of the algorithm, and then any tuning if necessary. And overall, this is the full pipeline that are defined in the various toolkits. And here are some packages that developers tend to use when building the recommender system with the inclusion of some of the popular toolkits that are available. And over the years, several toolkits have in fact been developed, which has been shown in the previous slide as well. And these toolkits have been developed to evaluate various algorithms, complex algorithms that have been developed as well. So our next question really would be, then what is the problem? And in this paper on the generalizability and predictability of recommender systems, we can see that an experiment was done, and we are able to see a very interesting results, whereby the item KNN, the most primitive form of a recommender system algorithm that has been developed, did in fact perform the best amongst the various complex algorithms with the different type of scoring that has been done. And this highlights a very interesting issue. That is why is such an simple algorithm performing better than all the other complex algorithms that has been developed? So it raises the question of the evaluation that has been done on the offline algorithms, which leads us to the gaps that we have identified. And mainly from Prof. Sun's survey from Take a Fresh Look at Recommender Systems from an evaluation standpoint, he highlights the pertinent case whereby instead of developing new novel matrices, we should instead really consider how these matrices are being created or defined to evaluate a recommended algorithm, and mainly how the neglecting of a global timeline during the evaluation can lead to two main issues that we will highlight: the data leakage and oversimplification of the user modeling. And in fact, in his other paper on the relook at task formulation in recommender system, we can also see that there is there is a oversimplification of a static user item interaction rather than a dynamic changing one, because of the removal of the temporal context in the evaluation and building of recommender systems in current toolkits. And in fact, what has been done is a review on 12 of the existing toolkits that have been published in top journals for this particular FYP project. And these toolkits are very popular toolkits that has been used over the years. And in these toolkits, we can summarize three big umbrella gaps that we can feel in that we aim to target. And these three gaps are the data leakage from the split, the ambiguous metrics being defined, and some inadequate online simulation. And to draw parallel to the pipeline, we can see that the data leakage from the split really pertains to the data split phase. The issue number 2 in the evaluation phase, the gap 3 would be in the train and evaluate phase. And overall, these are the three key points or three gaps that Streamsight aims to fill in. To briefly mention the problem of data leakage, to provide some contextualization, it would be to simplify the problem is an access to future data through some data partitioning whereby the algorithm has access to the future data before making a prediction on some past testing data, which would not be possible in a real life setting. And in the case of the ambiguous metrics being defined, the matrices currently do not have a temporal context, and there is ignorance to the temporal ordering, which also stems from the first gap that has been identified. That is where we test for the test instances. We do not respect the ordering in which the test instance exists on the timeline. Next issue is an inadequacy in the online simulation, whereby in an online simulation, typically what would happen is the platform would request for some recommendation from the recommender system, which would then be provided and then shown to the user. And what would happen is the ground truth will then later be supplied by the customer when he actually interacts with the platform. And this data would then be passed on to the recommender system for training, forming a feedback loop as shown. And this current dynamic is currently not captured in existing toolkits. And the objective of Streamsight would be to then fill in the gaps of these three gaps that we have identified, mainly to develop a framework to handle the temporal element, which toolkits are currently not doing, and to simulate a more closer data communication flow in the online setting as described before. So moving on to this design on how we can tackle these three gaps. In the first gap that has been identified, what we can do is we propose an implementation of a global sliding window. And how the global sliding window would be defined would be as such. We have the recommender system that will be trained on release data. And what would happen is the unreleased data would be then masked and then provided to the recommender system for evaluation purposes, whereby the recommender system will be predicting on unreleased data. And to give a concrete example, the dataset is first sorted in temporal order, and a window size is first determined. We then split the data set with the window size and with a fixed global timeline. In this case, t equal to which in this case we will set t to be equal to February. Now with this split, we have the background data which we will be using, which we will use to train the algorithm on. We then have the unlabeled data and the incremental data. And the unlabeled data will be used for prediction purposes, and the labeled data can be derived from the incremental data, which would contain all data needed to retrain the model. And we can iteratively run through this splitting mechanism across the data set, whereby we incrementally shift the global timeline forward. So in this case, in iteration 2, we shift the global timeline by 1 month. Then what would happen is we can repeat this across n iterations, and eventually we would be able to obtain this we will be able to obtain this four sets of data. Mainly three of them would be an array of split data. So the background data would be a single set of training data for the recommender system for the initial training. The unlabeled data would be unreleased data in the T+1 time step to evaluate the model on. The labeled data for evaluation purposes derived from the incremental data, and the incremental data will be released post-evaluation to retrain the model. So with that, we will now proceed on to the solution for the second gap that has been identified, which really to provide a temporal ordering during evaluation and temporal tagging to address the ambiguous metrics. In the case of the ideal, we will start off with giving an ideal evaluation, the ideal case of evaluation, whereby in this scenario, we have a ground truth for a given user and an algorithm, a recommender system algorithm that would perform a prediction for top three. Now, similarly, the algorithm is first assumed to be trained on the release data set. And in the testing set, what we would do is for every test instance, we would have the model to predict for the test instance respecting the temporal ordering of the occurrence of the test instance. So in this case, a prediction of three predictions will be done in its in the ordering of the test instance. And we can generalize this as a prediction of a set of n given users in a window, whereby the prediction is done while respecting the order in which the test instance occurs across all users in that particular window. So the circles not being aligned is intentional because the test instance has to be evaluated based on the actual occurrence of the test instance. And we can quickly see that there is a problem with this ideal evaluation, which is the computation needed to run this algorithm. And we can simply formulate it as the total number of predictions being the total number of test instances multiplied by the total number of users. And both variables depend on the window size and on the data set that is being used. And we can see that this problem does not scale as we increase the window set or the size of the data set. So we really need and to really formulate a scalable solution, instead of making one prediction for each user for each test instance, we can group the test instance into a window within the window size. So the temporal ordering of the test instance within a window is now then ignored. And we can limit the total number of test instances in that particular window by the algorithm's top k value, such that the prediction would be able to such that we'll be able to evaluate the prediction against the actual ground truth. And in this case, unlike before, for each user, the test instance would now be lumped as a single time occurrence, such that only one prediction is done for each user. And we can now reformulate the problem from the previous ideal evaluation into a total number of predictions that scales with the total number of users. So the computation time would have been reduced, and the performance gain can be contrasted when we assume the total number of test instances to be 10. And in this case, we can see that there is 10 times the compute reduction for this implementation that we have implemented. And in the next, to address the last and third gap that we have identified, what we can do is we can try to mimic the online data communication through streaming of the data set and to decouple the algorithm. So to illustrate, current toolkits currently provide a pipeline in which the algorithm is first trained and evaluated once. We have designed two different simulation to simulate the online data flow. So in our pipeline version, what is different is we would have Streamsight and the algorithm to run concurrently instead, which would instead to evaluate the recommender system. And we can quickly show an example whereby we have different phases. And in the pre-phase, what would happen is as similar as what was described earlier, the global sliding window would first be implemented. And what would happen is when the split has been done, we would then train the algorithm, and we would, after training the algorithm, we would then evaluate the algorithm. We would then train the algorithm. And in the next phase, we would perform an evaluation of the algorithm, whereby the RS would then be asked to predict on the unlabeled data set given, and evaluated based on the labeled data set derived from the incremental data set by Streamsight. And in the data release phase, the incremental data is released to the RS for training. And what happens is the global sliding window would slide forward for the next split. And we would then repeat this process of the evaluation whereby the RS would then be asked to predict again, and an evaluation will be done as similarly. So this process would run across simulating the case that we have described earlier on how the online interaction would be like. And instead of running in our second proposed communication, we can stream it through APIs, whereby we decouple the algorithm from the Streamsight platform separately. And this can be and we can briefly walk through an example as well. So what would be different is instead the algorithm will be instantiated separately from Streamsight. So its existence would be independent of Streamsight. And in a really quick example, we can see now the RS is only communicating with Streamsight as an entire object. And what will happen is we need to first register the algorithm with Streamsight, and subsequently the RS would then perform as if it was an independent standalone object, and Streamsight being the platform of evaluation for evaluation purposes. So the RS can request for data, and what will happen is the data will be fetched and returned to Streamsight. For the prediction case, the recommender system will request for the unlabeled data set, and what would happen is the prediction that is made would then be evaluated on Streamsight itself. So this is how we can stream the algorithm. We can stream the data as in the pipeline, and to decouple the RS from Streamsight itself, thereby mimicking a closer online data communication. And these are the results of the project, whereby now Streamsight is an open source project listed on GitHub. And we also have developed multiple user and developer documents for easy references and for viewing. We also have very easy installation provided for the users, where the users can install through the Python package or through a package manager. And we also provide type hinting through the development of code documentation with through supported IDE, whereby users are able to easily see the types of data and elements that are being used. Docstring supports are also provided such that the user need not necessarily open a web browser to view the documentation. Overall, we have developed 9 modules that would support the overall library and toolkit. And we also unify the interface, a simple interface which mimics that of scikit-learn. So an example given here is the load and split phase, which can be done in a few lines of code. The pipeline can also be easily defined as such. And in the case of streaming, these are the code that is needed to start the streaming and to get the model running, to get the evaluator running. And to obtain the results of the evaluation, we can simply call the type of metric that we want to obtain. And here's a short comparison of the toolkit, whereby Streamsight having implemented setting 1 and 2, which is a setting that observes the temporal observance compared to all other popular toolkits that we have done a literature review on, which are currently being used in 2024. whereby setting 1 and 2 consists of the global sliding window. As for future work, what can be considered is to include supporting attributes in the loading of the data phase, whereby currently we only consider these 4 items, the user item interaction along with the rating and the timestamp. So more data can be considered to overcome the issue of data sparsity. Next is Streamsight as an online evaluator, whereby we can provide Streamsight as an online service for other developers to make use of, similar to what we can see in Kaggle competitions, such that Streamsight is now a service, Streamsight now exists as a service. And to conclude the entire presentation today, what we have done is we have walked through the introduction, the background information of Streamsight. Thank you for listening.